Alright, AP Chem, here's your first video lecture for Chapter 7. Starting a whole new chapter. This is about the atomic structure and periodicity, periodic table. This is a list of the topics, or should I say a list of the sections we're going to cover in this chapter. It's quite a spread of topics, but we're going to have to trudge through. Today we're going to focus on sections 1 and 2, electromagnetic radiation and the nature of matter. So let's get started. Have you ever noticed when you're watching fireworks, for example, you see that those fireworks are different colors? Why are they different colors? And why do different chemicals give us different colors? One of the things you might have said is, oh, well, this one's made of lithium, this one has sodium in it. It has a different chemical signature, therefore it has a different color. The different chemical property results in this different color that we see. But why? What about that chemical gives us the different color? So let's move on. Electromagnetic radiation. This is one of the ways that energy travels through space. Not the only way, but it's one of the ways. Electromagnetic radiation. Electromagnetic radiation has three characteristics. It has wavelength, it has frequency, and it has speed. Wavelength, represented by lambda, is the distance between two peaks or troughs in a wave. Frequency, represented by nu, is the number of waves or cycles per second that pass a given point in space. So basically you sit down, pick a spot, and you count how many waves go past you in a particular amount of time. The speed is the speed of light. 2.9979 with a whole bunch more digits after that, times 10 to the 8th meters per second. A lot of people will just have you round that to 3 times 10 to the 8th meters per second. Now that is the speed in a vacuum. Okay, it will move slightly different speeds under different circumstances. All three of these characteristics are related by the equation c, the speed of light, equals lambda, wavelength, times nu, or frequency. Now let's continue to look at the nature of these waves. We see if this point of the wave passes and then this point of the wave ends in 1 second, if this amount of a wave passes your eyes in 1 second, you've had 1, 2, 3, 4 wave peaks. Okay? 4 wave peaks. So that's 4 cycles in 1 second. 4 cycles in 1 second. That is also known as 4 hertz. That's 4 times per second, also known as 4 hertz. Hertz is a unit. It is the exact same thing as 1 over second, or per second. If we have a higher frequency, we'll have more wave peaks per second. Okay? In this situation, we have 8 cycles per second. We have 8 hertz. Increase that even more, we'll get up to 16 cycles per second, also known as 16 hertz. You've also seen this depiction of the electromagnetic spectrum. We have the incredibly high energy light, the incredibly high energy electromagnetic radiation. We have the incredibly low energy electromagnetic radiation. And then we have this small portion, the small window, that is the type of electromagnetic radiation that you and I see using our human eyeballs. Not all eyeballs are made the same, by the way. Different mammals, different animals, even more than that, have different eyeballs. They're constructed in different ways, and they interpret electromagnetic radiation differently, and they see different parts of the spectrum. A lot of pollinating insects, for example, can fully perceive portions of the ultraviolet spectrum, which we cannot as humans. And that has to do with what their eyes are designed to interpret. One of the things that we see going on here, as silly as it might seem, we have energy being put into a pickle. The pickle is the medium. Energy is moving through that pickle. Now what's happening is energy is charging the atoms in the pickle. They're exciting the atoms in the pickle. And that excitation, the electrons jumping energy levels, results in an emission of light. And this can happen with most anything. This is really easy to see because there's so much sodium and other ions in pickles. The brining solution or the pickling solution has so much sodium that we see the wavelength, the type of light associated with sodium combustion. Energy can be gained or lost in integer multiples of Planck's constant times frequency. A system can transfer energy only in whole quanta. Okay, whole units. You have to have at least one quantum in order to transfer that energy. Now we're talking about very, very, very small amounts of energy here, the smallest possible, individual photons. So this quantum is very, very small. And so on our scale, the human scale, we don't really see this integer requirement of energy transfer really happening. You have to go to the incredibly small scale. And if you get down to this scale, you actually begin to see that energy has particulate properties as well. It has properties very similar to that of matter. Now we just said energy is quantized. As long as you go down to a small enough scale, energy exists in discrete quanta, and we call those quanta, those particles, we call them photons. And we can calculate the energy of a photon using Planck's constant and frequency. We can also substitute or derive a different version of this equation. It's the same statement. Planck's constant, speed of light, and lambda. We get the c over lambda by substituting that in for nu, or frequency.
The photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
Now, one of the many things that Albert Einstein left us was a statement that energy has mass. It's one of the simple conclusions that we extrapolate from E equals mc squared, because E represents energy, m equals mass. These things are both present in the same system. Energy has mass, matter is comprised of energy. But what that means for light, since that's the focus of this particular section, is that it has two natures. We see that light, electromagnetic radiation, exhibits properties of both waves and particles. Now, additionally, we also see that matter shows the characteristics of both particles and waves. But that's not necessarily what we're going to focus on here. We're going to focus on the electromagnetic radiation, not only having wave properties, which was known as the propagation of energy happens in the form of waves, but it was unknown until last century that electromagnetic radiation, light, or energy, also acts like matter. But you have to get to an incredibly small scale before you can observe these in full force. All right? At this point, I would like you to read sections 1 and 2 and attempt the end of chapter problems. If you have any issues completing the end of chapter problems, be sure to check out the sample videos provided. I will see you next period.